Thank you to the organizers for putting together this conference. It's been great so far. So I'm going to tell you about some work in progress. I wanted to put to appear or something, but I'll just be safer and say work in progress with Tin Suleiman-Pasic and Samson Chan, who are at Durham. Okay. So just a little bit of motivation. I'm sort of motivated by this question, general question of how we can discretize quantum field theories on the lattice while preserving as much of their symmetries and sort of global structure as possible. Okay. So on the one hand, this is of practical importance if you're actually doing, the Monte Carlo simulations. So if you already have the right symmetries and anomalies from the start in the UV theory, then you have to, do less fine tuning to sort of reach the desired deformation class and continuum physics that you're interested in. Okay. Now, I'm in this exclusive club that of people who do lattice gauge theory but have never done simulations. So really my motivation is that the lattice is a really nice concrete setting where we can just explore sort of subtle aspects of quantum field theory. Okay, so on a finite lattice, we're basically just doing quantum mechanics. And for those of you who are participating in this generalized symmetries program, I think like in recent years we've seen that by looking at symmetries from the perspective of lattice, we gain sort of new insights into the structure of symmetries and their anomalies and also how they emerge or emanate in the continuum. Okay. So the talk will be about the 2D chiral boson. So why this theory? Well, it's sort of a long-standing, interesting problem in the lattice gauge theory community of how to discretize chiral gauge theories. So take the gauge theory part out of it and just look at the word chiral. This is like one of the simplest chiral quantum field theories that one can imagine, right? And it appears in various places in the literature. It's, famous for appearing in the physics of the fractional quantum Hall effect, and it's very closely related to 2+1D Chern-Simons theory, as we'll see. Okay. And there's a sort of lore. Well, first of all, no one until very recently actually tried to write down a lattice theory for the 2D chiral boson. And maybe that's because they weren't interested in it, but I think more likely it's because of this common lore that, similar to the chiral fermion, that, it's actually just impossible to write down a 1+1D lattice regularization. Okay, so there are even some no-go theorems to this effect. So what I'm going to talk about is not going to literally be 1+1D lattice regularization. So I'm going to get around this a little bit. So why is this something to look at now? Well, myself and also the work of others, including Jingyuan, who's in the audience, we basically understood how to write down lattice discretizations of abelian Chern-Simons theory. Okay, and then there are other works recently that have explained how to write down lattice theories for the compact non-chiral boson, also in 1+1 dimensions, which preserve both momentum and winding symmetries, their mixed anomaly, and T-duality. Okay, so roughly speaking, if you take these two together, you get something like the chiral boson. So we want to sort of use some of the insights from these recent works and try to see what we can do with this chiral boson theory. Okay. So the first obstruction that we ran into, of course, is just basically Nielsen-Dinamiya, but adapted to this bosonic context. Okay, so I'll go through this very quickly. So basically, we're imagining that we have, let's say, continuous time. We discretize space. Momentum is then periodic, and if we write a local Hamiltonian, then we get a spectrum which is continuous in momentum space. Okay, and then you get a spectrum that looks like this, and you have two crossings of zero. You get a right mover and a left mover. Okay, so indeed, we wrote down some lattice theories that looked kind of chiral, but then in the end they had a spectrum that looked like this. And there have also been a couple of very interesting papers from a couple of years ago that, again, start with sort of chiral-looking ingredients, but in the end the spectrum is sort of vector-like. Okay. Now these models are very interesting in their own right, but we want something else. Okay, we also played around with some non-local models that gave us some spectra like this. Okay, but I'm not going to talk about those either. Instead, I'm going to get around the Nielsen-Dinamiya theorem in a way which is very similar to what David did in his talk this morning. Okay. The second obstruction we didn't realize until much later, and this already shows up in the continuum. Okay, and it has to do with the anomalies of this theory. So the chiral boson has a U1 global symmetry, and like the chiral fermion, there's an obstruction to gauging it. So if we try to couple the partition function to background fields, it's not background gauge invariant. But there's a difference with the chiral fermion, which is that this anomaly cannot be cured by coupling to a classical bulk theory. Okay, so usually what we do when we have an anomaly is we define the theory at the boundary of some, okay, 3-manifold, in this case, X, and we couple to gauge fields, classical gauge fields, which we extend into the bulk. Okay, then in the bulk, we write a classical anomaly inflow action, a symmetry-protected topological phase, if you like, that cancels, the non-invariance of the 2D partition function. So if you try to do that in this case, what you find is that the thing that you want to write is actually not a well-defined inflow action. So it's not well-defined because its coefficient has this k downstairs. K is an integer, which is some parameter that shows up in this chiral boson theory. Okay. So what this is saying is that the anomaly of this theory is actually not the anomaly of a 2D theory. This is sort of saying that secretly this theory is not quite two-dimensional. Okay, and similar considerations also hold for the gravitational anomaly of this theory. Okay, the non-invariance of the partition function is actually not just by a phase. Okay, so this gravitational anomaly cannot be cured by coupling to classical Trin-Simons, gravitational Trin-Simons term. Okay. So the upshot is that even in the continuum, this theory is not actually like really a 2D quantum field theory. So people call the chiral boson relative theory. It means that it's only defined as the boundary of a quantum field theory in one dimension higher, roughly. Yeah. So we should modify our goal. Instead of trying to discretize this theory as a, as a 1 plus 1D theory, instead let's try to find it at the edge of a 2 plus 1D theory. Okay. The difference with the 2 plus 1D theory that David talked about this morning is that the 2 plus 1D theory that we have to consider actually has a non-trivial Hilbert space. Like it's not an invertible field theory. It's not a, it's a genuine quantum field theory. It has its own Hilbert space, and we're going to use Maxwell Trin-Simons theory as this 3D lattice theory. So in the continuum, it goes back to this analysis in the 80s. It's well known that, if you quantize U1 Trin-Simons theory on a disk, for example, with appropriate boundary conditions, you get this chiral boson. For certain technical reasons, which I'm happy to talk about after the talk, just for time considerations, we use this Maxwell Trin-Simons theory. Okay. So I really have to point out that the same question, and actually a lot more, was studied on the space-time lattice by Jing Yuan and his collaborator. And so that's a really wonderful paper that I highly recommend you go and read. Here I'm going to not focus on the space-time lattice, but I'm going to look at the Hamiltonian lattice realization. Okay, so time is continuous, and I have a 2D spatial lattice with boundary. So let me describe the ingredients that go into this lattice theory. I'm going to warm up by just considering just a standard U1 gauge theory. Okay. So this is, you could call this the Hamiltonian version of Volan's formulation of U1 gauge theory in the lattice. Okay. So it consists of two canonically conjugate pairs. Okay, the first pair consists of the gauge field A and its canonical momentum pi. They both live on links, and they have canonical commutation relations. So if they sit at the same link, then their commutator is I. The second pair consists of a real scalar field phi. I'll call it the dual photon. And its conjugate momentum lives on plaquettes, and we call it the Volan field. We call it N. Okay. Here, this commutation relation is understood as follows. The label for N, you could label it by, let's say, the lower left-hand corner. So if these fields sit, on the same site, then they have a commutator I. So we impose a constraint on this Volan field. We say that it's actually integer valued. Okay, what that means is if you exponentiate it with an appropriate coefficient, 2 pi I, this should be the identity operator in the Hilbert space. On the other hand, from the commutation relations, this operator shifts phi by 2 pi. Okay, so phi and phi plus 2 pi have to be identified, and that tells us that this dual photon is compact. If I exponentiate this field, this operator, that the interpretation of such a thing is that it's the monopole operator, local monopole operator in this 2 plus 1D U1 gauge theory. Okay. So far, so good. So here's the lattice Hamiltonian for this sort of Velan version of Maxwell theory. So it's basically just B squared plus E squared. Okay. Where I have this lattice beta, which is related to the dimensionful continuum gauge coupling. Okay. So the gauge invariant quantities are like the lattice magnetic field, this dA minus 2 pi n, and the two electric field components, which in this case are just the conjugate momenta. Okay. If we want to take a continuum limit, we just send beta to infinity, and we basically land on free Maxwell theory in 2 plus 1. Okay. So what happens when we consider Maxwell-Chern-Simons theory? Not too much from the Hamiltonian. Okay, so the B squared term is the B squared term. The only thing that changes is the definition of the gauge invariant electric field. Okay, so instead of just involving the conjugate momentum pi, now we have to add a little leg involving the gauge field, which just points in the sort of rotated direction. Okay, so that's the only difference for the Hamiltonian in this Maxwell-Chern-Simons theory. But there are also constraints that define the physical Hilbert space. I already talked about the constraint that says that the Velan field was integer valued. We also have a constraint that tells us that we're really doing compact U1 gauge theory. Okay, so I want integer, 2 pi times the integer shifts of the gauge field to be a gauge redundancy. If you stare at the Hamiltonian, that means that the other fields have to shift in this way. So one can find an operator V, okay, such that if I take the exponential of 2 pi I times some integer large gauge parameters m times this operator V, they implement this transformation. Okay, and that operator we want to constrain to be the identity operator on the physical Hilbert space. So that gives us a constraint. The constraint just tells us that this V operator is itself integer valued. Okay, so this thing lives on links, or is associated to links, and it's just some kind of funny combination of the dual photon difference, nearest neighbor difference of the dual photon and all of the other operators. Okay, so this thing is integer valued. Consistency of this constraint, in other words, the fact that these constraints have to commute, tells me that this Chern-Simons level K has to be an even integer. So that's where the level quantization shows up. All right. We also have invariance under just ordinary sort of small gauge transformations. Okay, that shifts A by d lambda. Conjugate momentum also gets a shift. And this is implemented by just exponential of basically the Gauss law. Okay. So what is this Gauss law? It's the sum of a bunch of terms. So the first term is the divergence of the conjugate momentum. You could think of that as like in pure Maxwell theory, we would just have this term. This is just the divergence of the electric field. But because of this Chern-Simons coupling, we have to add some extra terms into the Gauss law. This plaquette term and some terms involving this Velan field. Okay, so this thing commutes with the Hamiltonian. It commutes with itself on different sites. So that's our Gauss law. Okay. One thing I want to point out is that this theory does not have a magnetic symmetry. And that's not like something that we got wrong on the lattice. That's also true in the continuum. Okay. So notice the Hamiltonian doesn't have any terms that involve the dual photon. Right? So that means that n, the canonical conjugate of the dual photon, commutes with the Hamiltonian. So it's a conserved quantity. And if we construct the gauge invariant charge associated with this conserved quantity, that's actually just corresponds to like the magnetic flux through our 2D space in the continuum. Okay, it's just the sum of all of these n's on the whole lattice. Well, it turns out that this sum is actually just the sum of all of the Gauss laws on this 2D lattice. Okay, and that vanishes identically. Here I'm assuming we're working on a torus, we have periodic boundary conditions. Okay. So the associated charge of this would-be symmetry is just 0, so it's actually not a symmetry. Okay. And relatedly, the thing which would have been charged under the symmetry, namely the monopole operator, is actually not gauge invariant. Okay. It doesn't commute with the Gauss law. This monopole operator, it has charge k, but the charge is sort of split into nearby sites into fractions k over 2. Okay. Fine. So what does this theory do? The Hamiltonian is just quadratic, so we can diagonalize the Hamiltonian very easily, and we can look at the spectrum of local excitations. And it looks something like this. Okay. So the key feature is it's gapped. And if we take the continuum limit, take the lattice spacing to 0, this spectrum just becomes the familiar Lorentz invariant spectrum of Maxwell-Chern-Simons theory, where the photon mass is this combination ke squared over 2 pi. Okay. So that's the spectrum of gapped excitations. But there are also some ground states. Okay. So this theory has topological ground state degeneracy. And the way we see that is we look at certain line operators. Okay. So I pick some curve on the lattice, and I construct the exponential of this operator, where I build it out of that same v that I defined before. You get an operator that looks like this. Okay. It's some kind of ribbon on this 2D lattice. So this operator commutes with the Hamiltonian. If I take its kth power, I get the identity. That comes from the fact that the little pieces v were integer valued. And it's topological in the sense that this operator is the same, literally the same on the Hilbert space, same operator on the Hilbert space if I deform the contour slightly. Okay? This deformation is achieved by just adding and subtracting the Gauss law, essentially. So these operators also have interesting commutation relations. So if I take two of them and I commute them past each other, I'll get some zk phase, which depends on their intersection. Okay. So on the torus, for example, I can put one of these operators on one cycle, put another on the other cycle. They only commute up to the zk phase. And so the entire torus Hilbert space, in order to realize this algebra, is k-fold degenerate. Okay. So that's the ground state degeneracy. And these line operators are just the anyons of this Maxwell-Chern-Simons theory. Okay, so that's all stuff in the bulk. And now I just want to describe what happens when we introduce a boundary. Okay, so just to sort of illustrate the idea, I'm going to take a particular boundary condition. So I'm going to look at a rough boundary here at y equals 0. So I'm letting the system just, it's a half infinite system. It goes up to y equals infinity. Maybe I have a finite number of sites in the x direction. Okay. So in terms of the gauge invariant quantities, this boundary condition is basically telling me that the parallel component of the electric field is 0. Okay. And crucially, we only apply the Gauss law on the bulk sites. Okay. Heuristically, if I tried to impose the Gauss law on the boundary, well, the full Gauss law sort of doesn't fit at the boundary, so we don't impose it there. But actually, even if you wanted to impose it at the boundary, you actually couldn't, because they don't commute. Okay. So we don't have a Gauss law at the boundary. What that means is that part of the gauge symmetry actually becomes a global symmetry at the boundary. Okay, so in particular, the magnetic symmetry that I talked about before that actually wasn't there in the bulk Maxwell-Chern-Simons theory now becomes a bona fide global symmetry. And up to the Gauss law, the magnetic flux through this half-infinite lattice is equivalent to this magnetic charge, which is just pretty much, it's boundary localized. Okay, this thing commutes with the Hamiltonian. Okay, so what does it act on? It acts on Wilson lines that terminate at the boundary and then end somewhere in the bulk. Okay. They can end somewhere in the bulk because we have essentially charged matter fields in the bulk, namely these monopole operators. So this monopole operator carries charge k, but it's split between k over 2 here and k over 2 here, and so we can attach Wilson lines that terminate at the boundary to get something gauge invariant. Alternatively, we can take one of those anyons and terminate it at the bulk and let it end on a monopole operator. Okay. So both of these operators have charge 1 under this global U1 symmetry. Now I can write this global U1 symmetry, or the charge of this U1 symmetry, as a sum of some gauge invariant charge density. And that gauge invariant charge density is just the Gauss law, what you get when you try to push the Gauss law, right, down to the boundary. Okay. So let's look at the commutator of these charge densities. Their commutator takes the following form. Okay, so it's I over 2 pi k, and then it's a next nearest neighbor difference of delta functions. Okay. So this should look familiar. This is just the lattice realization or lattice discretization of the U1 Kac-Moody algebra. Okay, so in the fractional quantum Hall effect, we look at these, commutator of charges, which in the continuum would be like 1 over 2 pi dx phi, and their commutator is the derivative of the delta function. Okay, so here we just see the lattice discretization of those commutation relations. And we also actually get the correct normalization factor. So we have this k downstairs, and this coefficient is precisely the fractional anomaly coefficient of the U1 anomaly that I mentioned at the beginning of the talk. So this is the chiral anomaly. Okay. So when we saw this, we were very excited because really this is the indication that the boundary theory is chiral. We realized a lattice discretization of this chiral algebra. But just to be sure, we just wanted to solve the theory essentially. Just look at the spectrum and make sure that it's actually chiral. So to do this, I look for modes with some particular, some fixed frequency, and I also Fourier transform along the parallel direction where I still have translation invariance. Okay, so here phi is just the collection of the gauge invariant operators. Okay, so the Heisenberg equation of motion for this phi takes the form of a transfer matrix equation. So this transfer matrix, it sort of evolves these operators at some layer y plus 1 down to the layer y. Okay, we still have to impose the Gauss law on these modes, but essentially we just look at the spectrum of this transfer matrix, okay, and decompose into the eigenmodes. So this is a 3x3 matrix, so it has 3 eigenvalues. One of them is 0, but actually that mode does not obey, doesn't satisfy the Gauss law, so it's unphysical, so we can ignore it. And then there are 2 remaining, and their product has magnitude 1. So given one of these eigenmodes, if its eigenvalue has magnitude which is less than 1, okay, from this transfer matrix equation, it's telling us that it's decaying towards y equals 0, which means that it's growing into the bulk. Okay, so that's a growing mode. If the magnitude is equal to 1, then it's just a bulk mode, like the wave function is just, magnitude is just constant. And if the magnitude is larger than 1, then it's a decaying mode. Those are the ones that we're interested in. So here's a plot of the transfer matrix spectrum. Okay, here I just chose some particular value of the lattice coupling constant. Okay, so within these sort of purple bands between these dashed lines, we just have bulk modes. So both of the non-zero eigenvalues of the transfer matrix have magnitude 1. Okay, and then everywhere else they come in pairs. One with magnitude larger than 1, one with magnitude less than 1. Here I'm just plotting the ones with magnitude larger than 1, which correspond to the decaying modes. Oops. Okay. Now we need to impose boundary conditions. So recall, the boundary conditions were just that the parallel electric field was 0 at y equals 0. And there's a unique eigenmode of the transfer matrix that satisfies this boundary condition. And it only exists for particular values of the frequency and the momentum that sweep out this curve. Okay? And this curve is just telling us the dispersion relation of the chiral edge modes. And you can see it's, first of all, completely independent of the coupling constant of beta. And it actually even depends on the sign of the Chern-Simons level. That's exactly what you expect also in the continuum. And okay, it's chiral. So this really is realizing, this is a chiral theory. Okay. And what's nice is, well, if we're interested in the continuum limit, for example, we take beta to infinity and we zoom in on the low momentum modes. Okay. And then what you find, well, first of all, this just becomes a linear dispersion relation. But we can ask about how localized is this edge state. And in the continuum limit, it turns out that just by looking at this eigenvalue of the transfer matrix, this mode decays indeed exponentially with the scale set by the continuum mass gap. Okay. But if we start to give this mode more momentum of order 1 over the lattice spacing, then it starts to delocalize more and more until we hit momentum pi over a, in which case it's just completely delocalizes and merges with the bulk spectrum. Okay. If we send the momentum past pi, then this mode becomes the growing mode, which we've omitted because we just have this y equals 0 boundary. So if I consider a system with just a single boundary component, I just get this right moving mode. If I have something like an annulus, then I'll have left moving mode on one boundary, right moving mode on the other. But for this analysis, I'm really just looking at this half infinite system. So that's really all I wanted to say. We succeeded in finding indeed this chiral edge mode of this 2+1D lattice String-Simons theory. You could say that this model gives a lattice gauge theory realization of the fractional quantum Hall effect. Okay. And we're still sort of learning about the fractional quantum Hall effect using this lattice discretization. So for example, since I have a little bit of extra time, here I talked about operators that have charge 1 under this global U1 symmetry. But there are also operators one can consider that have charge 1 over k. So those are the operators where you send one of these anyons. Here I took an anyon to the kth power and I ended it on a monopole operator. One could just take one of the anyons and terminate it on a fractional monopole operator, sort of improperly quantized monopole operator. Those states would have charge 1 over k under this global U1. And those states are precisely corresponding to the states which are created by the minimal vertex operator in the chiral boson theory. And what this just is really telling us is like, well, actually those operators, they exist in a sort of twisted Hilbert space. And all of these sort of subtleties that are secretly there in the continuum, they're just like really in your face in this lattice discretization. So those are things that we're just exploring. There are other questions that we'd like to answer, like how robust is this to changes in boundary conditions? Okay, so in particular, I chose boundary conditions such that we got this U1 global symmetry. One could imagine just adding terms to the boundary Hamiltonian to explicitly break the symmetry or consider some other boundary conditions. Well, the fact that in the continuum, this theory in the bulk has a gravitational anomaly is supposed to be enough to ensure that the boundary is gapless and chiral. So if we could somehow show that even when we break this U1 global symmetry, we still have a chiral mode, that would be a strong indication that, we have something at least consistent with gravitational anomaly in the continuum limit. Okay. We'd also like to investigate different geometries, for example, a finite system like a disk, but also a strip geometry like this one, where you have a left and right mover. This will just give you a alternative discretization of the compact boson with the momentum and winding symmetries. It'd be interesting to compare to existing lattice discretizations of that theory. Okay. And then finally, something that I was chatting with Jingguan about is what happens when we start to relax some of these constraints on the Hilbert space. So this will help us connect to the condensed matter literature, where often they want their gauge symmetries to be emergent, so they just add terms in the Hamiltonian that penalize or essentially energetically enforce various constraints that in this model I put in by hand. So I'll stop there and take questions. Thanks.
Thank you, Theo, for an awesome talk. Questions? Okay, I saw one hand go up here first.
So there is one very special case, that is when K is a perfect square. In such a case, you can condense some anyons in the bulk, make the bulk trivial, get rid of the bulk, and essentially the boundary theory becomes an absolute theory. So is there something special that you see in this lattice construction?
Just for the U1 case? I don't think so.
Because U1 level K, if K is a perfect square, is a diagram of Witten theory.
Okay. I thought that for NK...
It's Swiss, the diagram of Witten theory, yes. But it contains a Lagrangian algebra. No, if K is a perfect square.
Well, to answer your question...
Yeah.
To answer your question, I don't see anything...
Yeah, this is what I meant, yes, okay. Yeah, okay. It has a gravitational anomaly, I agree, but it's a... Yeah.
And the K-form symmetry and an anomaly or non-anomaly is manifest.
Do you agree?
No.
Don't you agree that there is a non-anomalous one-form symmetry?
Maybe to discuss later. I think I saw a question from Arkady.
When you're saying on the boundary, you mean it's two-dimensional boundary, right? Or
Yeah, so time is continuous, and I consider like a spatial boundary.
But I wonder about what about chiral fermion? Would you consider this?
Okay, good. Yeah, so recall that the level quantization condition I got was that K had to be an even integer.
Okay. Yeah.
But one could also consider Chern-Simons theory where K is an odd integer. Those correspond to essentially fermionic theories. So yeah, I should have put that here as something also to explore. So one can sort of enrich this model by coupling to some fermions, and then the operators that create this chiral mode will indeed be fermionic. And we can consider sort of like a bulk boundary sort of bosonization, if you like.
So in principle, did I get it right? That you mean that in principle it's possible, right, to go there?
That's right. Yeah. But I also want to mention in the case of fermions, one doesn't need. This theory has an actual Hilbert space in the bulk. There are non-trivial operators that exist in the bulk, and strictly speaking, in the fermionic case, one doesn't need that. So one can, for example, do what David did and have a much simpler theory in the bulk to realize this Weil fermion boundary.
Okay, thank you.
It's a really beautiful talk. But since you mentioned fractional quantum Hall state, I'm curious, is there any progress on the case when K is odd? For instance, if you want to get a Laughlin state.
Yeah, so yes, in the bulk, this is something which was worked out by Tin and I and also Jing Yuan in the case of these double theories.
Right.
Yeah, so essentially what you'll see is that like these monopole operators, for example, monopole operators get attached to some Majorana fermions, and one has to think about what are their boundary conditions. But yeah, it's something that we haven't looked into, but I think is fairly straightforward.
Okay, thanks.
More questions? Oh. Okay, go ahead.
Can you do non-abelian Chern-Simons theory?
Ask Jing Yuan. So Jing Yuan has a proposal for essentially generalizing the Lamb type formulations, which is really what is what we're leveraging to write down this theory to the non-abelian case. But as far as I know, those also I don't know if they have a status as a Hamiltonian, in the Hamiltonian formulation. But yeah, stay for Jing Yuan's talk.
We planted you in the audience to advertise Jing Yuan's talk. Other questions? Oh, I see one in the back.
So one thing that's a bit hard to see in the continuum is like robustness to disorder. Is there some way to introduce disorder here on the lattice and maybe try to see how that affects the physics?
Yeah, that's a great question. I don't know. I'll ask you the question. I'm not sure how one exactly would introduce disorder. In general, I mean, yeah, I just don't know enough about the literature there, but yeah, I know that people say that disorder is very important for fractional quantum Hall physics, but somehow here we're not really writing down a microscopic theory of spins, although it is a different kind of lattice theory.
Yeah, in one version of the heterotic string, you'd like to have 16 chiral bosons propagating on an E8 cross E8 lattice.
Right.
What's the what's the three-dimensional theory for that one?
Well, you don't need a three-dimensional theory for the E8.
I know you can fermionize it, but if you want to do it the hard way.
Yeah, so, okay, I guess alternatively, take, 8 copies. I don't think we need E8 times E8, but let's say we take 8 copies of this. Does something magical happen when we couple them together using the E8 lattice such that somehow the bulk disappears?
Yeah.
That would be very interesting to see, but I'm not sure. Yeah.
Okay, I have a question. In the beginning of your talk, you had various formulas with an epsilon in them, and I was wondering what epsilon is. I don't know if you commented.
Oops. Epsilon is just defined in such a way that this is what it means.
Whatever does that.
That's right. Okay. So it's kind of you rotate and then you sort of have to shift. If you just rotate pi, you get something on the dual lattice, and then you have to shift it over to the original lattice. And here I'm choosing a convention where I shift down and to the left.
Okay. Yeah. Other questions from the audience? Okay, then I have one more. I'm sorry, I'm abusing my position here. So you mentioned that you see the topological ground state degeneracy here in this approach. Was that for any beta, or is that in some limit where you turn off Maxwell?
No, that's for any beta.
Should I be surprised by that or not? Because naively for generic beta, it's not a topological theory.
Yeah. So this is not a topological theory, but we have an exact one-form symmetry.
All right,
and we
spontaneously broken.
Yeah. Okay. We have its anomaly. This is just telling you that this one-form symmetry is anomalous. And that's for any beta.
Indeed. Thank you.
Okay, so this may be a naive question, but in Polякov confinement, you have a compact QED, and then you have a domain wall, which is interpreted as a flux, confining flux tube. Right. So can you have this sort of thing here, since you have a periodic photon as well?
Yeah. So not without additional matter fields. So the problem is that the monopole operator is not gauge invariant. Right. I mean, this is also the case in the continuum. In Chern-Simons theory, the monopole operator has charge k. And so actually, this was studied by Rob Pisarski back in the mid-80s first, I believe. And he was precisely asking your question, what happens to Polyakov mechanism when you add a Chern-Simons term? And basically it breaks down. So this theory has a one-form symmetry. So in principle, there could have been stable flux tubes, but they're screening instead. Now, if you start to add particles with, let's say, charge k, then you would have a gauge invariant monopole operator, which you could imagine maybe condenses and gives you confinement. But that's still unexplored. I'm not sure. It may well be explored, but it's definitely not explored in these lattice theories, but it may well be explored in the continuum.
Okay. Any other questions? Okay, if not, let's thank Theo one more time.